Okay, let's dive right into this explainer. Have you ever wondered how an artificial intelligence model can stare at a massive, chaotic pile of data and somehow accurately predict a medical diagnosis or even consumer behavior? Well, you're definitely in the right place. Today, we're going to completely demystify one of the absolute most popular algorithms used in healthcare research right now. We'll trace its evolution from a single, heavily flawed decision tree all the way to the incredible predictive power of a vast, randomized forest. Here is our quick roadmap for today. We're going to cover the basics of machine learning, take a look inside a single decision tree, explore something called the overfitting problem, enter the random forest, and finally, unpack exactly how that forest works behind the scenes. All right, starting off with section 1. What exactly is machine learning? To put it simply, machine learning is just a subset of artificial intelligence. It focuses on algorithms that allow computers to literally learn from data and make predictions, completely without being explicitly programmed step by step for a task. You aren't writing code that says, if A happens, then do B and then do C. Instead, you feed the algorithm a ton of data, and it goes in and finds the patterns all by itself. It's a total game changer, which is exactly why it's such a hugely popular tool in healthcare right now for predicting patient outcomes. Moving right along to section 2, inside the decision tree. Fundamentally, a decision tree acts as a classifier. Its whole goal is to separate outcomes, like, say, figuring out whether a patient has tumor subtype A or subtype B. It starts by throwing everyone into a single parent node, and then it searches for the best possible feature to divide that group up. For example, rather than using biological sex or BMI or diabetes status, the tree might mathematically figure out that patient age is the strongest predictor. It then makes a clean, perfect split, separating patients who are under 60 from those who are 60 and older. So, how do we actually use this? Well, once the tree has built, newly diagnosed patients can get a prediction just by running their data down the branches. Let's say we're evaluating a brand new 71-year-old patient. They simply flow down the right side of this tree into the node for patients 60 and older. Because 78.6% of the historical patients in that specific terminal node have subtype B, boom, the tree confidently predicts that our new patient also has subtype B. It's highly flexible and honestly very intuitive. But you might be wondering, how does the tree actually know that splitting at age 60 is the absolute best move? Well, the tree decides where to make these splits mathematically using purity measures like the Gini index. The goal here is to create daughter nodes that are as pure as possible, meaning all subtype A patients end up in one node and all subtype B in another. Looking at the Gini index, a score of 0 means a perfectly pure node. Awesome. But a score of zero point 0.5, that means the node is totally unhelpful, basically a 50-50 mix of both subtypes. So the tree is constantly calculating, weighing these scores, and relentlessly hunting for that optimal, perfectly pure split. Which brings us to section 3. And honestly, the main villain of our story, the overfitting problem. If the ultimate goal is absolute mathematical purity, we run into a major issue. When do we actually stop splitting the tree? In theory, we could just keep slicing and dicing the data into smaller and smaller branches until every single terminal node hits a Gini index of 0. But what happens when we take this massive, highly specific, overgrown tree and try to use it to predict outcomes for brand new patients? The absurdity of doing that becomes obvious pretty fast. Imagine we're trying to predict who drives a large SUV, just based on a small sample of people in a room. An overgrown tree will start off normal, splitting on logical things like your profession or how many kids you have. But to reach perfect purity, it starts finding completely spurious random chance associations. It will literally create a rule suggesting that you drive an SUV simply because your favorite food is pizza, or because you happen to have a summer birthday. It hasn't learned the real underlying patterns at all. It's literally just memorized the exact people in that specific room. And this is the fatal flaw known as overfitting. Because single decision trees are so highly flexible, they act as what data scientists call high-variance classifiers. They overfit the specific training data they were given, capturing completely random noise and spurious associations by pure chance. The result? You get a model that performs absolutely flawlessly on historical data, but totally bombs when it tries to accurately predict new, unseen observations. And frankly, the entire point of building a predictive tool is to use it on the future, not the past. So how do we fix this? That leads us right into section 4. Enter the random forest. Instead of relying on one wildly overgrown and unpredictable tree, a random forest builds an entire ensemble. Usually, we're talking anywhere from 500 to 1,000 separate decision trees. By running our patients' data through all 1,000 of those trees and then averaging their predictions together, the random forest completely stabilizes the crazy high variance of a single tree, giving us a highly accurate generalized model. Okay, final section. Let's look under the hood. How does the forest actually work?
Now hold on a second. If we just feed the exact same training data into 1,000 trees, wouldn't we just end up with 1,000 identical clones of the same flawed tree? Well, this is where the magic really happens. The random forest forces independence among the trees in a couple of really clever ways. Step 1, it uses something called bootstrapping, which means it randomly samples the original data with replacement to create totally unique training sets for each tree. Step 2, at every single split, it randomly selects only a subset of predictors to even look at. And finally, step 3, it holds an election, counting the votes of each of those uniquely built trees to determine the final prediction.
This averaging mechanism relies on plain, brilliant common sense. I love how the source material puts it. It is the same reason a doctor may take your blood pressure 3 times at the same visit to get an average reading. Just like that, averaging the votes of hundreds of randomly generated trees smooths right out those wild variations and spurious connections that plague any single model. The errors in individual trees effectively just cancel each other out. Which leaves us with a pretty fascinating thought to end our explainer on today. The random forest essentially proves, mathematically, that an ensemble of slightly flawed, restricted models, when combined, creates an incredibly accurate and stable prediction. It's literally the ultimate expression of the wisdom of the crowd. So, if averaging random perspectives solves high variance in machine learning, how might ensemble thinking help solve other chaotic, unpredictable problems in our own lives and decision-making processes? Definitely something to think about. Thanks for joining me for this explainer, and as always, keep learning.